I'm Jason Herbert, and this is A Reckoning. Our guest today is Matt Strassler. Matt, you just wrote a book. I have it in front of me. This one.
Excellent.
Actually, I love this so much, and I have to tell you a thing here. The book is Waves in an Impossible Sea, How Everyday Life Emerges from the Cosmic Ocean. This is actually the second part of the podcast series that we do. We do historians of the movies and talk about film and stuff like that. And I kept thinking about different movies as I was reading your book, actually. But in a lot of ways, your book kind of encouraged me to start doing this Reckoning version of this podcast because I saw it and I was like, I got to talk to this guy. This seems so cool. And it's frankly, as a historian, so far out there from what it is that I do. I want to talk to him. So you were, I think, the very first person I reached out to when I started thinking about doing this thing. It took us a little bit to get it going, but I'm so excited to talk to you today, man.
Well, I look forward to it.
All right, let's do it. You want to introduce yourself and tell us like who you are and what you do, and we'll just kind of jump in from there?
Sure. I mean, I on the surface, I'm just a fairly garden variety theoretical physicist with an expertise in particle physics and in the mathematical language of particle physics, which is known as quantum field theory. Mm-hmm. And, I studied that in college and graduate school and went on and became a professor and was a professor for quite a lot of time. I'm now sort of semi-retired. I maintain affiliation with Harvard University now, and I continue to do some research, but I also have always been interested in explaining these wonderful things to my friends, whether they wanted to hear about it or not. And so it seemed sensible at some point that I would write a book about it. And I started thinking about it in 2013, 14, and it finally came out in 2024.
Well, I have to tell you, I walked out onto my back porch this morning to let the dog out. It's snowing. I didn't know it was going to be snowing, and I looked out and I saw the snow coming down, and I thought, waves. That was literally the first thing I thought. I was like, oh, these are waves. So we have so much to talk about. I guess maybe the first thing I want to get into before we get into your book is how did you become a physicist? A garden variety physicist, mind you. But what drew you in? Like, was this a class you took in college that kind of got you going, or was this something that happened as a child where you're like, I really started to want to understand how the world works? Like, how does one become a physicist?
Well, I mean, my colleagues have many stories. My story happens to be one that does, in fact, reach back to early childhood. We had a family friend who was a professional astrophysicist. And so he and my dad would chat, and we didn't see them that often. But when we did see them, the astrophysicist in question would show my dad some of the pictures that he was working from. And I was 4 and I sort of tagged along, and I saw these amazing pictures of galaxies. And I don't know. I was hooked right there. Right. So I started asking lots of questions, and my dad would answer questions, and I would ask more questions, and my dad would answer the questions, and I would ask more questions, and my dad would run out of answers. So he'd give me books, and I would read the books, and I just kept swallowing information as quickly as I could in about this. And, at some point in my early teens, discovered that particle physics and quantum physics in general was an area that really was profoundly counterintuitive, and that the world that as it actually exists is so different from the way it seems. And that really started to hook me into that particular subfield. And then, I just went on, there was college, there was then graduate school, and then postdoctoral life, and finally faculty position. And so at a certain level, it was kind of a straight shot from that interest at age 4. But each of us has our own. Each of us in the field has our own little, personality quirks and strengths and weaknesses. And I was always interested in music, also, and so I always played instruments. And so as I was learning physics, I always had that particular lens to see it through. And it turns out that lens proves to be very helpful and useful in coming up with a way of looking at the world that is easier to convey to non-scientists, which is part of what the book does. And it also was always very good at sort of philosophical thinking, sort of stepping back from a problem. I'm not very good at doing hard calculations. I always ask a friend to do those if we're working together. You have to know your strengths and weaknesses. And one of the things I'm strong at is looking at the big picture, seeing relations between things that are not necessarily obvious to everybody else. And so again, that sort of put me in a good position to be a teacher of a certain type and a writer of a certain type, which again, I think, is why I ended up writing this particular type of book, not most of my colleagues.
Yeah. The book is produced by Basic, who put this out. And it felt like this kind of book was really kind of directed at me, maybe a person who's not a specialist in physics, but curious about understanding these things. And, I think the cool thing about what you're doing with this book is kind of talking to us about this real high level stuff, but in a way that, you don't need a specialized degrees in physics to get. And so you're talking about, right, man. First of all, thank you for that. But because I have to tell you, as a guy with history degrees, we are famously anti-math. We were like, no, we don't even want to talk about dates over here. But so I said, okay, I'm going to sit down and talk to a physicist about this book, and that means reading it first and putting on that aspect of my hat. But it was so easy, Matt, to get into.
Oh, that's great.
And so, it was very inviting. The book it's really terrific. And you're talking about your love of music, and I'm like, you said that, and I'm like, oh, that's why you're using the guitar to explain, so much of this movie, because it's the way sound moves and things like that, explains so much of it. Did you find there was a different aspect of your own brain you were engaging when you're thinking about, this is how I write to the general public versus, say, colleagues or students that you might have and so forth? How does that work?
It's a great question. I mean, certainly, there are, on the one hand, there are different ways, different modes of communication that one has to use, depending on who one's talking to. And that's a general statement. I mean, even if I'm just talking to a friend, I'll speak differently depending on what that friend's particular background happens to be, or how much we've talked about things in the past. So obviously, in choosing the tone for this book, that was a question which had to be thought through very carefully, because I wanted it to be, on the one hand, accessible to a broad audience, and on the other hand, I didn't want it to be useless for a person who actually had read about these things before. So that finding that balance was interesting and challenging. But part of the reason that I felt I could do it was that it's kind of the way I talk to myself, in a way. It's about how do I strip away all of the things that I don't actually need to focus on in the mathematical equations. I mean, doing physics means you're dealing with mathematical equations and concepts, and you're trying to understand how to use them in order to make predictions for experiment, or you're trying to go backwards from experimental results and try to understand how to make equations that will describe them. But in the end, if you want to understand things well, it's always better if you have a simple picture that you can describe to yourself in a simple way, that you're confident the math will conform to. And if you really want to get it right, that takes some skill. So that's something I have needed for myself as a physicist, because, as I said, I don't calculate very well. I mean, I calculate better than the average person, but I don't calculate better than the average physicist. So, so that meant that in order for me to understand some very complicated subjects, I needed to simplify them down for myself in a certain way. That same skill proves to be the skill that's necessary to write a book, where you strip away all of the unnecessary jargon and all of the unnecessary extra details and go down to the core of what really matters. And that's what I've tried to do in the book. And hopefully I've succeeded.
No, I really think that you have. And obviously the vast majority of my followers are historians, people who are interested in history, who come to me from that regard. And here was the cool thing I found as I was reading your book and some other folks that I've had on here, was that it's a departure of what it is that I do, is I'm writing my own work. And I find that so completely refreshing. It's like, okay, this is another way to think about things. This is really, in my mind, this was really enjoyable as you were kind of walking me through like these processes and stuff like that, and say, wait a second, this isn't actually how, this is what we're taking for granted, but this isn't actually how things work. And then just kind of laying things out, kind of building towards the end there, kind of coming back and so forth. It was I hate to use a music analogy, Matt, but it kind of felt like there was familiar refrains as we kind of went, as you go through the book, and then you kind of build to this coda, at the end. There is structure to the book, and one learns about structure from music and poetry and theater, and that kind of structure
is important in constructing, I think, any work of art, including a book about physics.
Yeah, there's a thing you can relate to, and I'm so glad that you did that, because I actually sang on this very podcast last night. Nobody wants to listen to that structure. So we were talking about the big band revival of the late '90s. If you remember that was
so from the big band to the Big Bang. I see. Okay, very good.
That's a book waiting to be written, Matt.
Maybe so.
All right, let me ask you this before we jump into the book, or maybe, you've been doing this for a while now, and people come to you, all kinds of folks. Are there popular misconceptions about physics that you hear? This might take a bit.
Wow.
We have
how many hours do we have?
Right. Okay. What are some of your favorite or most common misconceptions that people come to you and say, hey, what's the deal with this, right? What are common things that you often hear that maybe you have in your own career said, oh, well, let me explain to you how this actually happens and stuff like that?
I mean, there really are so many. I think one of the most common is that people have the idea that Einstein said that everything is relative. That was the point of the theory of relativity. Everything's relative.
Right.
That was not the point. In fact, the first person to really talk about the relativity of motion in particular, which is really the relativity of how different observers moving relative to one another will perceive the world differently. I mean, a simple thing like, if you're on a train and there's an orange on the table in front of you, the orange looks stationary from your point of view. But obviously from the point of view of somebody off the train, the orange is moving. Okay, it's simple things like that, just differences in perspective from the fact that, different people are moving different ways. So, relativity, a physicist's idea of relativity is to try to understand if the world looks this way from one person's point of view, how is it going to be different from somebody else's point of view? How do I translate between one person's perspective and another? That's what relativity is about. And the first person to really think that through was Galileo, 300 years before Einstein.
A little bit before, right.
Yeah. So there is a Galilean theory of relativity. And some parts of that survive to this day. And what Einstein did was to realize that it's actually more complicated and more subtle than Galileo, or indeed any of us in ordinary life, would think. Because Galileo was sort of capturing things we kind of know, but making them more precise and noticing some very interesting things about them. Einstein said, well, it actually, time doesn't work the way you think, and space doesn't work the way you think. We even have different perspectives on space and time, even though it's not obvious from our daily lives. And that has a huge impact on the way the world actually works, and explains some big mysteries about the speed of light and things like that. So what Einstein was doing was, on the one hand, changing Galileo's theory of relativity, but he was also not saying, and nor was Galileo, that everything is relative. There are some things that aren't. So he was telling you what's relative and what's not relative, and that's also very important.
I feel like you said earlier, like everything is relative. Like it almost gets used as like just a cheap explanation. People are like, oh, it's relative. Right. Yeah, it's fine. All right. And things like that. But I want to ask you this. We still refer to it as a theory of relativity, right, Matt? Mm-hmm. So why theory, and like why isn't it the law of relativity yet? Like how
do the words work? Yeah. It's a great question, because I mean, a lot of things which I talk about on my blog and also on in the book, and in a recent article in New Scientist, I wrote a whole story about it, is about language. We underestimate the importance of language in its role in science. It plays a role in how scientists communicate with one another. It plays a role in how scientists think about what they're doing. It plays a role in how we communicate to non-physicists. And the words that we use amongst ourselves are a dialect. Just like any, movies have a dialect and sports have a dialect. Right? I mean, if you don't speak baseball, you don't know what strike and out and base actually mean, right? And we have the same issue in any field, and science is not alone. So the word theory in science doesn't mean what it means in English. That's part of the confusion. And it causes all sorts of problems. I mean, just think about all the arguments over the theory of evolution. Well, what scientists mean by theory is not the same as what it sounds in English. In particular, theory in English tends to mean a speculation, something we're not sure about, something that is just an idea, a possible explanation, but it hasn't been verified yet. So it's not it's theory as opposed to, let's say, fact or something more confident. Mm-hmm. Whereas the word theory in science retains, it sort of has two meanings. It continues to mean what it means in English sometimes, but usually what it means, and certainly what it means when one talks about the theory of relativity or Newton's theory of gravity, is one is talking about a set of equations and a set of concepts that go with those equations that teach you how to use the equations to make predictions for nature. So it's a statement about a mathematical structure and a conceptual structure, which may or may not have been verified by experiment up to this point. So when Einstein first developed the theory of relativity, it was a theory in the English sense and a theory in the physics sense. But then as experiments verified that, oh, this thing works great, it became remained a theory in the physics sense. It's still a set of equations and a set of concepts that we use to make predictions. But it became, as close to a fact as anything in science ever is. I mean, the word fact sort of implies that it could never be shown to be incomplete. This is just true. Whereas any scientific idea, all we know is that it's worked for every experiment we've done so far, and it covers a huge amount of ground. But it could be someday that with better technology, we discover, there are circumstances in which it's not complete. And that was true of Newton's theory of gravity. It turned out it wasn't complete. And we needed Einstein's to make it better. And then you asked about law, which is another interesting word. Yeah. So the word law has gone out of favor in large part in theoretical physics in the last at least 50 years. I don't really know the history of that word, to be honest. The idea that nature has laws is something we still use in sort of colloquial speech, but we tend not to call something a law these days. That's not without exceptions. So, in a sense, the word law doesn't really have a strict definition, but typically, when one speaks of a law of physics in the modern day, it refers to a specific equation, as opposed to a sort of general framework.
Okay.
So Newton's three laws of motion, they are three equations or things that can be stated as equations, which together form a theory of motion. So they're sort of pieces of a theory. And so, you can say E equals mc squared could be called the law of energy mass equivalence, but you don't have to. And so most physicists don't. We just call it E equals mc squared. But one doesn't want to get lost in the linguistics, right? But in the end, the question is, what are the equations you're using? How are you using them? And how are you making sense of them? And how are you comparing them with experiments? And how well do they work? And the words we use often get in the way. Language is great for communication. It's also great for miscommunication. And many times the words in science cause confusion about how science actually works, simply because they're used differently in English.
Yeah, that's the thing I've often been fascinated with is I wonder how the evolution of the human way of conceptualizing things via language, the way we express and understand the world has actually affected how we see the world and things like that. And I think, you talk a little bit about this early on, and this is maybe not a linguistic thing, but you actually talk about maybe the dangers of common sense. And I'm kind of wondering if that's another thing we can kind of touch on as well. People listening in on the pod now are just going to be afraid to ever voice a thing ever. But can we talk a little bit about, because one of the cool things about the book is that you're taking all of these things we maybe take for granted or us make these assumptions on based upon the ways that we see the world and go, wait, there's something else actually going on completely different here. So
it does relate to language because the words that we use reflect our common sense and also shape the way we think about it. So when we talk about seeing, what it means to see a tree, we tend somehow to think about it as though we just look, or the world, just shows itself to us, right? Our eyes are like windows. We just see the world as it is.
Sure.
And there are so many elements to seeing which we leave out of that. The structure of the process of seeing is really very complicated. Light has to come from somewhere. Let's say it comes from the sun, travels across space in a few minutes, bounces off the tree, goes into our eyes, is absorbed by molecules in the eye, transformed into by the workings of the eye, is processed by the eye, and through that processing, at the end of it, an electrical signal is sent to the brain, and then the brain processes those signals. And finally, at some point, a picture becomes available to our consciousness. So when you think that process through, the word to see is leaving a lot out, and that can have big consequences. So we imagine that what we see is what is there. Seeing is believing, right?
Oh, yeah.
But
maybe not.
The eye is not a window. The eye is a processor, like a digital camera. It takes information in it. There's some of the information it doesn't record at all. Some of the information it processes and turns into electrical signals. And that's what the brain receives. And then what the brain does with it is it scrambles it around. And in the end, what we, quote, see is far from what is actually out there. And that explains a number of things. For example, white light. Okay, we all learn that white light is made from all the colors of the rainbow, right? Sunlight is white because it's got all the colors, and that's why when raindrops split the light, and we see everything from violet all the way up to red. Where's pink? It's not on the rainbow. That's a clue. Where's brown? That's not the rainbow.
No.
Okay, so that's funny. All right, but here's another funny thing, right? Then you go to some class where you learn that the way people make white on the computer screen that you're looking at is they combine red, green, and blue. No yellow, no orange, no violet. They just combine red, green. There's just three colors, right? There's three phosphors.
Okay.
And, so why does that work? How can it be that white light contains all the colors, but you can make white light with red, green, and blue? And the answer is that white light is not a thing. It is an experience. White light is the experience of white is created in the brain. And there are multiple ways to make the brain experience white. One of them is to give it all the colors. One of them is to give it certain combinations of colors. In fact, there's an infinite number of ways to make the brain experience white. And pink is an experience. Brown is an experience. These colors don't exist in the world. They're just combinations of colors which make the brain give you the experience of pink. Now, this is far from obvious. Why would we? I mean, we humans we didn't come into the world guessing that.
Sure. And
we assume that seeing is believing. We assume that what we see is what is there. But it's almost never true. And that's the lesson of the last 4 centuries of science, especially the last century and a half, is that the world is very different from the way it appears. And at almost every level, common sense, and I don't mean common sense about everything, because common sense about how to interact with other human beings, okay, it's very helpful there. But common sense about the physical world is almost always wrong. And so when we try to understand the world through our senses, we have to come in with the knowledge that there's much more going on in the world than we can experience through our senses, and even our senses are scrambling what's out there. So that's important to know if you want to learn about how the world actually works.
Matt, I feel like you've actually just given every guy in the world an out whenever his beloved asks them if this dress makes her look fat. And you say, actually, no, it's the light reflected and I'm being processed. And we can just work their way out. But
the answer is always, I'm not competent enough to answer this question.
That's fair. I can't do the computations. It's too high line for me. I want to ask you, okay, this feels related because you talk about this in the book quite a bit, which is a fib. And this is another thing for you guys listening in right now, a PHIB, a physics fib.
I have invented this term.
I love this term. I would steal it if I could. I love it. Can we talk about what a fib is?
So, I mean, for anyone who has ever read a book for non-experts about science, or has watched a TV show about science, chances are that they told you something that wasn't true, and they didn't do it because they wanted to lie to you. They did it because there's only so much time, and you have to simplify things. Okay, but there are different types of lies, right? I mean, there's the little lie around the edges where you just omit some of the complications, but what you're saying is basically true. You're just leaving out the details. But then there are lies where you really say something that isn't true because the true explanation would take just too long and involve things that people don't generally know. And so you invent something that kind of sounds plausible, even though it's wrong. And that's a fib, because now you've actually said something that is really not true. And I don't know. It always makes me think of the Holiday Inn Express commercials. You remember those where staying at this hotel, it won't make you smarter, but it'll make you feel smarter. Well, that's what fibs are for. They're to make you feel like you understood it, but they're not intended for you to understand it, right? They're not true. And sometimes this is harmless. I mean, okay, fine, does it really matter? But sometimes fibs about the world, because they create so much cognitive confusion, because, I mean, after all, it might sound plausible for a moment, and then you go home and you try to think about it again, and you realize, wait a second, I must be stupid. I can't figure this out. Well, no, you're not stupid. They told you something which didn't make logical sense. So, this is really not something I think that physicists should do on a regular basis. If they have to, they should do it. But whenever you don't have to do it, you should take the time and do the honest work to think of a way of saying it that isn't fraudulent. Even if it's a minor fraud, just avoid that. You don't. If you work hard enough, you can usually avoid it. And so one of the things which I tried to do as hard as possible in the book was both correct a number of fibs that are widespread, and to avoid adding any of my own. And that requires thinking very carefully about how can you explain a complicated idea in the simplest possible, most intuitive possible way. And sometimes it's very hard, but at least you're not saying something to people which is better. I think in many cases it's better to say this is too complicated to explain than to pretend to explain it and cause widespread confusion.
Yeah, it's almost like just trust me. This is what's going on, and just moving forward, right? And you're
sometimes,
right. Like it feels to me like you were explaining this almost like you'll see in films. And I was thinking about either time travel. Like, oh, we've got to warp around the sun. And this starts to become like a trope in films or something like that.
Right.
Or gravity. And I'm thinking about the films Interstellar, perhaps. And I know, they were really trying to dig in on the science on that. So I don't want to critique that, but it's because I appreciate the effort. But it's like, you've got to put this into a way the audience will understand and can like mentally move on from, so they can get to the other.
Yeah, it's a story, right? You're telling a story. You don't want to get hung up on some technical scientific details. That's not the point.
Right. I had a director, Edward Zwick, was on the pod. I did Glory and some other stuff, and I'd asked him about, and this feels very similar, Matt, where I was like, how do you make the decisions when you're doing a film about a historical subject, about like when to quote unquote stray from the accuracy of a thing, right? And he was like,
big question in historical films, right? They're never true, right?
Right. And they're not supposed to be, right? They're not documentaries. And he had said, he used the word necessary truths to kind of explain. It's like, you're trying to tell the necessary truth behind this story, but you also need to keep people's eyes on the screen so you can get to that, to the point you're trying to make. And I felt that was far more eloquent than I ever could have said it myself. And it feels like maybe in some ways, the fib kind of feels a bit like that.
Well, I mean, this question comes up in historical films too. I mean, it's one thing to leave things out.
Right.
It's one thing to create things around the edges that make a good story, but don't actually create any falsehoods.
Sure.
It's another thing to make stuff up.
Sure.
And from my perspective, even for historical films, that's crossing a line. And it shouldn't be necessary. That is to say, you should be able to make a story where if the person came back from the dead, they wouldn't actually sue you for libel. And I don't want the universe to sue me for libel. So I want to tell it as it is.
Sure. And that becomes the challenge to either the physicist or the historian who's writing the book. Always. Or the whomever, right? It's like,
that's right.
How do I push myself to find a way linguistically, narratively, mathematically to tell? I mean, and again, it kind of comes back to why you wrote this book in the first place. It feels like it's like, hey, here's what's going on here.
The key was, of course, to avoid math and
sure.
and to find ways, even though words are very problematic. I mean, the reason physicists use math is not only we do calculations, but because they're unambiguous or much less ambiguous anyway. And so we're going to make far fewer mistakes and have far fewer miscommunications if everything is written down in mathematical language. That, of course, is useless to the non-expert. So the problem is, can you get away from the math but retain the precision of the language?
Right.
Can you find ways of expressing things that, okay, it's never going to be perfect for every reader. Each reader is going to have a few things they don't quite get. It's part of why I have the blog. There's a lot of supplementary material to the book. It's on the blog, and people can always ask me questions there, because I know somebody's going to get stuck on page 84 because there's just one paragraph they're not reading the right way. But I'm available to fix that. But the key was to try to make the book as precise and clear and accurate as possible so that it's a coherent, logical whole. And once you absorb it, it can stick with you because it's not full of contradictions the way a book that has a lot of fibs in it will be full of contradictions.
Right. I don't want to give away the entirety of the book because I want people to read it, but I do want to talk about maybe a couple terms here that people are probably have heard of. They know what this is, or there's a familiarity with it, and then it's almost, at least in my own experience before reading, I go, oh, okay, cool, and then I can move on. So I want to ask you, can we talk about the Hadron Collider, and also the Higgs boson? Like, can we talk about what those are for people who are listening in, and really kind of maybe dive into a little bit about the mysteries, the auras around them, and like how you explain what they are, why they're important to us.
Yeah, I'll give you a little context, and we can
Please.
sort of. A hadron or hadron is just a word for particles like protons and neutrons, which are found in the nucleus of an atom. It's just a more general term, and why they use that instead of just proton collider is a detail we don't need to go into. But and it's not the first collider of protons that we've had. It's maybe, I don't know, 5th generation or something. But this is a big one. So we call it the Large Hadron Collider. Very inventive name. And by big, we mean it's in a tunnel that's about 17 miles around. Crosses the border between Switzerland and France. What's really important is not that it's big, but that the collisions of the protons that occur inside of it have more energy than any previous machine. And the idea of proton collisions, the reason you want to smash these protons together, is not that you're interested in what's inside the proton. We know what's inside the proton. What you're interested in is that there's something that can happen in Einstein's relativity that doesn't happen in ordinary life, which is that you slam two things together, and if they're of the right type, they can disappear, and the energy that of the collision could be used to make other things that weren't there before. So it's a little bit like, imagine that you slam rocks together and you expect to make a whale. But that's kind of what we do. We slam things together to make new things. And the fact that so these collisions are not a destructive process; they're a creative process. You're trying to make something new, and then you're trying to study what it is that you made, which can be very difficult because the thing you make may only survive for a trillionth of a second and then fall apart into other things, and you have to work backwards from the things that last longer to figure out what you made in the first place. So it's not necessarily an easy game. But that is the strategy that we are using at these types of particle accelerators. And the Large Hadron Collider is the biggest and most energetic, has the most energetic collisions of any of its type. And it had many goals, it has many goals, but its primary goal was to get a grip on what was, at the time, one of the great hypothetical ideas, one of the great speculations about how the world works, which is called the Higgs field. Now, a field for a physicist is something that's sort of integrated into the universe. It's found everywhere. The Higgs field is one of a bunch of fields. The electromagnetic field is another, the gravitational field. There are things called the electron field, which have to do with electrons, and quark fields, which have to do with quarks. Okay, lots of details. But the point is that this is an aspect of the universe in some way.
Good. We
don't know exactly how to think about it. But anyway, it's certainly something that's across the universe. And it plays a very important role, at least according to this speculation, which comes back to the 1960s. The idea was that there is a problem in the math that it's very hard to explain how, given the math that we had at the time, the 60s, how it could be that the electron could have a mass. Some problem in the equations. The details don't really matter, but it's very important that the electron has a mass. The fact that the electron has a mass is responsible for the existence of atoms. If you take the mass away from electrons, then they just go flying off at the speed of light, atoms fall apart, you and I don't exist, the planet doesn't exist, there's no life anywhere in the universe. So it's important that the electron has a mass. And we were at this position, we didn't actually understand how it was possible. And the Higgs field is a possible solution to that problem, where the way that the Higgs field affects electrons causes them to have the mass that they do. And not just the electron, but it turns out for essentially all of the elementary particles that do have mass, they get it from this Higgs field, according to the theories of the 1960s and 70s. And again, that's theory in the speculation sense at this point. So now the question was, how can you test this? Mm-hmm. And it became, so one of the ways you can test whether a field exists is you try to whack it and make it wiggle. Right? And a wiggle in the electromagnetic field is what we call a photon. It's a particle of light. And similarly, a wiggle in the Higgs field is a particle. It needs a name. We'll call it the Higgs boson. So the Higgs boson is the name of the particle that is a ripple in the Higgs field.
Gotcha.
And if you discover the Higgs boson, if you discover examples of this type of particle, that's evidence that the Higgs field exists. Because after all, if you find a ripple in something, something must be there. So, the purpose of the LHC was to try through these proton collisions to make any new particles that might be out there, but in particular, to try to make sure we could look for this Higgs boson. Mm-hmm. Or if the speculation were wrong in some way, to try to find whatever else replaces it. Right? We didn't know for sure we would find the Higgs boson. Maybe we'd find other things. Or maybe there were multiple Higgs bosons. So a lot of different questions that we had when this machine turned on in 2010. And the purpose of the machine was to look for these things, find them if they're there, study them in detail so we can understand how they work. And okay, well, it looked for them. It found them in 2012. There are Higgs bosons. There don't seem to be any others, or at least not easy to make. And the original simple hypothesis that there's one Higgs field and that's what gives masses to everything, that is still the best game in town as far as the data. And so that's why the collider was built. That's what it has discovered. And the thing we know now that we didn't know before it is that, yes, the Higgs field is not just a nice idea. It is actually a central ingredient in the universe, without which electrons would not have their mass and without which we would therefore not exist. So,
who gets to use the LHC? I'm getting to use my like.
It's a good question. It's very different from a telescope, right? A telescope, like the James Webb Telescope or the Hubble Space Telescope, can be used by many different astronomers. And what they do is they apply for telescope time. They say, I want 2 days to point the telescope at this particular very faint object because that's how long I need in order to be able to get a good image of it. What you do the rest of the time, I don't care.
Right.
But I need 2 days at a time. A particle accelerator is very different because all it does, leaving aside some specialized things it does occasionally, all it does most of the time is smash protons together with protons. And all of that data is collected into one giant pile. Or rather, there are collisions that occur at 4 different locations around the machine. And so there are 4 different piles of data because at each collision point, there are big detectors, big experimental devices, really giant devices that are the size of small office buildings. And they collect the data from the collisions and they store it. And a couple of thousand people work on the biggest 2 of those detectors each. And those people are the ones who, they don't operate the machine that makes the collisions. That's a group of machine physicists. But the people who have built the experiments and collect the data, they are the ones who then can take this giant pile of data, which is all collected, and decide, okay, let's analyze the data in this way, or let's take this part of the data and analyze it that way. And different groups of people analyze it differently. But they're not getting different amounts of time on the accelerator. They're taking the data from the accelerator and using it in different ways.
Wow. Is it? Did they just then farm out the they farm out the information to other people who want to analyze this?
It's a complicated fraud issue, actually. Yeah.
Yeah. Because it's exclusivity, right?
There is an exclusivity question. After all, they built the detector and they collected the data. So shouldn't they get a chance to analyze it? Why should they hand it to everybody else? And to some extent, this is what's the right way to say it? This is something which kind of almost takes care of itself. That is to say, the data is so complex that if you don't have expert knowledge, the kind of knowledge that I have, but probably less than 100 people in my field have, you can't really use it anyway. So the experimenters have an advantage, which is there are not that many theorists and certainly no non-experts who can do anything with this data. It's that complex. But it is true that they don't want somebody like me, who is an expert, digging into their data on the first day and maybe asking a question and finding something that, they collected the data, right? They should have a chance. So it used to be that the data was so complicated, and this political issue of I don't want to let other people look at it meant that the data remained private. At this machine, they are making the data public, but with a delay, which I think makes perfect sense for several reasons. One is it takes time to clean it up. It takes time to store it in a fashion that other people can use. And they deserve the opportunity to analyze it in detail. And analyses take 2 or 3 years in many cases. So typically, the data is being made public, but only after several years. And they're still working at how to do that in the most effective way, because it's hard to publish all the data in a useful form. There's a lot of it.
Yeah, I mean, for this to be so revolutionary, 2010 is when it came on?
That's right.
Right?
Yeah.
I mean, it's 15 years. It doesn't see. It's not that old of a machine. Am I correct? I mean, it's like there are things to work out still.
Typical machines of this sort have an interesting life cycle.
Okay.
So, and this goes back, at least a couple of decades into the past. They will run for. They will take data for a certain period of time, maybe a couple of years, maybe 3 years. And then they will turn off for a little while, and people who are analyzing the data will analyze. But they will fix things that broke, and they will upgrade things, and they will do things so that the next time they turn on, they can do more.
Mm-hmm.
And they'll keep doing that. They'll have these 2 or 3 year runs where each time the run is better than the last one because they're either at higher energy, or maybe the collision rate's higher, or maybe the detectors have been improved, or maybe all of the above.
Right.
And so that means that they get, even though it's the same machine running again and again, it's not really quite the same machine. It's a better machine each time. And once they get to a point where, okay, there are no more improvements that are really going to be that helpful, can't go any higher in energy, can't get the collision rate any higher, can't really do much with the detectors without a huge expense, then people start, or rather, before they get to that point, when they can see the end is 10, 15 years away, they start thinking about, okay, what are the other machines that we might want to build, and why would we want to build them? And so that's kind of the life cycle of these machines, and it's been going on like that for quite a while.
I have to go car shopping this afternoon, which isn't really a thing I typically share. I'm not looking forward to it. It's snowing, as I told you, and I don't want to go shop anyway. But you have this fascinating analogy. I think you told me that a teacher had explained to you as far as the movement of physics in relation to money.
Oh yes, yeah.
Can you? Because
where you're going with this, but now I see.
I am Captain Segway over here, Matt.
Okay.
So I'm wondering if we can explain that, because I loved it. I loved I love this analogy.
I'll start without the car part, but
Please.
We'll bring the car part in.
Then we'll find out what color I'm getting. Yes, absolutely.
Yeah, whether it's pink. So
I see the colors.
So, when we speak in ordinary language, just ordinary English, we speak all the time about, I just don't have a lot of energy today. Or she has such good energy. It's a vague way of speaking. We know it's vague. I mean, can you imagine if I said, she has such good energy, and you said, how much good energy does she have? I mean, that would be a ridiculous question, right? You've never asked.
It would interrupt everything. You go.
Right. It's a total not second.
Right.
Yeah, it's impossible. So
good vibes. Right.
Yeah. I mean, how many vibes, right? So, but in physics, again, the word energy means something related but different.
Mm-hmm.
For a physicist, energy is something which can be precisely measured. So when I say an electron has energy, I don't mean, hey, an electron's got energy. No, I mean it has a very specific amount of energy that I can measure and satisfy certain equations like E equals mc squared if the electron is stationary. And those are things that can be observed and tested. And in particular, one of the really important things about energy is that the amount of it, at least in most ordinary experiments, I mean, when you get to black holes, things get complicated, but let's not go to black holes. It's just in all the experiments we would do on Earth under normal circumstances, the amount of energy you start with is the amount of energy you end with. Precisely. We have lots of evidence for this. So, it's like money in that sense, except you can't print it. The amount of money you start with, okay, it goes places. You may lose track of it. But however much money you started with, it's now in somebody else's pocket, or some of it's still in yours. Mm-hmm. And if you want to buy more things, you need to find a way to obtain more money from somebody else's money. You need to, get paid from some company's bank sheet. So, money is something which we keep track of in great detail. And if you do analysis as an accountant, everything should line up to the penny. And this is true of energy as physicists mean it. Everything should line up perfectly. How this relates to cars and language is that the way we talk about what happens with a car is not the way a physicist talks about what happens with a car. So we, in ordinary language, will say, well, gas, that's fuel, that's energy. You go to the gas tank, you go to the gas station, you fill up your gas tank with some fuel. Now you have some energy that you'll use when you press an accelerator. That that energy gets used to make the car move, and then you run out of gas. The energy's used up, and in the meantime, the car slows down and stops because it's run out of energy. That's not the way the physicist says it. The physicist says the fuel has energy stored in its chemicals. In its chemical bonds. The way the car works is its engine breaks those chemical bonds, and through the clever engineering of a car engine, turns that into the process that makes the car move. And now the car, through its motion, has energy. The fuel's energy has been turned into the motion energy of the car, and then the car slows down. Why? Because of friction, because there's friction of the wheels against the road and the axles against the other parts of the car. And that takes the car's energy of motion and turns it into heat. Still energy. It's just energy you can't see. You might be able to feel it if it's warm enough. And so in the end, the car comes to a stop, but the energy isn't gone. The energy is now in heat that's been dispersed into the environment. So the fuel had energy. It went into the car's motion, and then it went from there into heat that got dispersed. And the amount of energy in that heat that has been dispersed is the same as the amount of energy that was taken out of the fuel, to the penny.
So here's my question then. If energy is, can be transferred, does that mean that is there a finite amount of energy that, Matt, or is energy created? If energy is the same across the way, is there ways to come up with more energy, or is it just constantly a certain amount of energy universally that is just constantly in a state of being transferred from here to there or whatever?
This is actually a slightly complicated question if we think about the universe as a whole. So let me answer it in 2 steps. So if you just think about our local neighborhood, let's say the sun, the planets, and we don't worry about stuff that's further away than that.
Okay.
Then the answer to your question is, there's a finite amount of energy. And where do we get energy from? We get it from the sun. The sun has a process of nuclear fusion going on inside it, where it's using hydrogen to create energy in the form of light and other forms of, this is staying in the form of light, and in the process turning that hydrogen into helium. Mm-hmm. And someday it will run out of hydrogen. That's why the sun's lifetime is finite. And then it will have to burn some helium, and then it will burn some other, but eventually it's going to run out of fuel, and then it's going to die. That's why the sun will die. It has a finite amount of fuel. There's no more energy. Once the available stores of energy in the hydrogen have been used up to make helium, and in the helium, so you make lithium and so forth, it's gone. Now, what about us? Well, we obviously get a lot of our energy from sunlight. There is also energy stored in the earth. There's radioactivity that occurs in the earth where atoms of a certain type, thorium or uranium, may disintegrate and pump out some energy. That's why the earth still has volcanoes, even though it's billions of years old, because there is heat being generated inside the earth. But that also is finite. Even when the sun goes, the earth will still not be frigid entirely because it'll still have some heat internally. But again, that's finite. That will go away. So over 100 billion years, it's all going to be gone. The sun will be out. The planets will have run out of energy. There's nothing for life to live on. There's no energy to drive the processes of life, because life is about taking an energy in the form of food and using it to do things like procreate and move around. So once there's no source of energy, life comes to a stop. Now, so yes, any star in its planetary system, sure, there's a little bit of starlight that comes from outside, but that is way too little to drive to drive the processes. So yes, the fuel in this planetary system is finite. Now, where did it come from? Right? Where did this? Well, it came from the Big Bang. The Big Bang was a big energetic thing. It had lots of energy, and we haven't used it all. Where did that energy come from? Okay,
That's
now we get into the really complicated questions because we don't know. And when it comes to gravity, and particularly some sort of universe-wide questions about gravity, the issue of conservation of energy no longer quite applies the way it does in the ordinary context that we live in. There's something more subtle, where space and time and energy are, they can behave in more complicated ways. And on top of that, when you're talking about the really early part of the Big Bang, you're talking about potentially need to understand about the quantum nature of space-time, which we don't understand. And so it isn't clear whether energy in those circumstances can be created from nothing or not. We don't really understand the beginning of the universe. So all I can tell you is that, yes, we can sort of follow the flow of energy from early in the Big Bang till today and into the future. But we don't know about what happened at the very beginning.
I want to ask you a question about how we process things. Because here's the question I want to get down to. We talk about the Big Bang. And we're talking about the way that we perceive the world around us and things like that, and conceptualize and express that through language, through mathematics equations, stuff like that, right? Maybe language is a verbal equation. I don't know.
Probably not, but I mean, I'm sure a philosopher of language could find a way. But that's probably not a useful way to think about it.
Probably, right? But here's my question, Matt, which is, do you think that humans have the cognitive ability to figure these things out, to come down, like you're talking about, like there are parts of the space-time equation we don't get, we don't understand, right? We don't understand. Either we haven't been exposed to enough data, seen enough things, have the right equipment or whatever. Is it possible for humans do you think it's possible for us to ever get there, to understand it?
I just don't know. I mean, if you ask yourself, could a goose figure out how baseball works? Right. This is a famous analogy. Could a goose figure out how baseball works? Right. At some point, probably not.
Right.
You put a bunch of goose in a baseball stadium. They can watch for years. They can do all sorts of. They can ask all sorts of questions. But can they really understand it? Can they understand why anybody would play it? I mean, so there are aspects of the universe that could very well lie outside our cognitive abilities. But it is true that our cognitive abilities are very flexible, and so we don't really understand what their limitations are. It's just important to be cognizant of the fact that they might be there, that there might be things that are very confusing about the universe. That the problem is maybe not quite the goose in the baseball stadium, but it's a little bit that. And certainly, an example of that is we have quantum physics. Again, everyone's heard the word quantum. Almost nobody. And a lot of people heard lots of fibs about it, and then a few things about it which are not entirely wrong. But the fact of the matter is that quantum physics is so complicated that theoretical physicists argue about it. And maybe complicated is the wrong term, because actually there are some things about quantum physics that you can state in very simple language, although not in the language that we could fit into a podcast, but that are not that hard to state, that nevertheless challenge the human mind at a level that 100 years after and indeed this year is 100 years since its first appearance in physics, we still do not understand whether the issue is that we're not smart enough to understand how to think about it. There are aspects of it that don't make sense, and in fact, the theory is incomplete or missing something, or something else. So, we don't know. Maybe it's just that it is a logical, sensible thing, and we are just not capable mentally of wrapping our heads around it entirely. The amazing thing is that despite all the things we do not understand about it, we have been very good at finding math that describes it, or at least the elements of it that we understand, that it's so good that we're, look, here we are talking about building quantum computers, and we do, we use lasers all the time, and we understand the quantum physics of protons and neutrons and atoms and so forth in great detail. These are things that we have accomplished, despite not being able to wrap our heads around the bigger picture. And so it may be that it's always going to be something like that. There'll be aspects of it that we understand really well, and some bigger picture questions that maybe will be too hard for us. But of course, there's no way to know but to try.
I feel like every time I go to the dog park and I see this flock of Canada geese over there, I'm going to look at them differently now.
Try to explain quantum physics to them. See how it works.
Listen, you're trying to explain quantum physics to me, and I'm hanging on.
Well, same here.
Before we were prepping for this pod, it's like, hey, there's all this stuff I'll talk to you. And you're like, yeah, that's going to take some time. And I feel like we've only really scratched the surface of the things that are in your book. And in a lot of ways, that's really good because I want folks to come to this because I really, really took so much from it. But I think ultimately the big question I have for you, Matt, as we kind of come to a close here, is how do we make, talking about understanding the cosmos, right? Understanding these waves in the impossible sea, like how do we make this personal? Essentially, how does understanding physics and seeing all of these things around us, how does this help us understand ourselves?
Well, there are, I think, many wonderful layers to that question, a number of which I addressed in the book, but let me pick a couple. So one of the things I think we've learned from our work in modern physics is that, we are not these, even though we often draw things as though we are, we're not sort of made from these little grains of sand that somehow stick together and are floating around in this empty universe. That is the wrong picture. The mathematics of quantum field theory, the mathematics of modern physics, teaches us that actually the world is sort of made out of space and fields in a way that we don't really understand. But what is for sure is that we are made from ripples in those fields. Now, those are the same fields found here and on the moon and on distant planets and halfway across the universe. Everything in the universe appears to be made from ripples of the same thing. And so the laws of the cosmos, first of all, are the same as the laws of outer space, let's say, are the same as the laws in this room. And the same as the laws in every atom in my body. Mm-hmm. And so the cosmic is the personal. We are part of the cosmos. We are integrated into it. We're not just floating around in it. We're made from ripples of it.
Right.
And so that's one very, I think, critical way in which understanding the cosmos is really understanding our relation to it is, I think, really important for human beings to know. To have. Right? So some recognition that it's all one, right? The new agey, we're all one. Well, it's actually according to modern physics, some aspects of that are true with some precise statements, right? And then I think another element which comes back to what we were talking about earlier, the verb to see. When you understand what is out in the cosmos and how we relate to it, how our bodies relate to it, how aspects of it, are so important to us. I mean, even these really esoteric things like, oh my God, quantum physics. Okay. Yeah, quantum physics. Every time you look at anything, your body is absorbing light, one photon, one particle of light at a time. That is a manifestation of quantum physics. You do not see without quantum physics. And the process by which you walk across the floor, you take it for granted. Well, you don't fall from the floor because the floor is solid. It looks solid, feels solid. Except that it's mostly empty space. And the only reason it behaves and looks and so forth as a solid has to do with a combination of your physiology, how you see and feel the world, but also with the quantum physics that makes the floor behave as though it's solid, even though it and your body are mostly empty. So understanding how the world works completely changes, first of all, it goes completely against common sense, but it also completely changes your understanding of what it means to sense the world and what it means to experience the world and what it means to engage with the world. And so I think that is another sense in which understanding the cosmos in the sense of not outer space specifically, but just the workings of the cosmos, which are the workings of our bodies, changes the way we understand what the world is, how we relate to it, what our brains are actually telling us, what our senses are actually doing, and how often common sense is not a good guide, but the reality is even richer and more interesting than what common sense tells us.
I love it. Matt, I really love the book. I've told you that so many times because it's absolutely true. It's just for me coming to this stuff, there's always a hesitance if you're not a specialist in a field to open up a book and say, hey, this is something that I'm completely foreign in. But you just make this stuff so accessible to me, I think to most any of the reader, because if I can get it, I think other folks can too. And talking to you today has been just an absolute blast. Thank you so much for being here. This has been awesome.
Thank you. Good. I'm glad you. It's been a great conversation. I'm really glad you enjoyed the book.
Awesome, buddy. Thank you so much, guys. The book is called "Waves in an Impossible Sea: How Everyday Life Emerges from the Cosmic Ocean." I'll put links to this on Blue Sky and everywhere else on all the social medias and also on the Substack. Matt, this was awesome. Thanks so much.
Thank you.